In this video, we present MS3D++, Ensemble of experts for multi-source unsupervised domain adaptation in 3D object detection. Deploying 3D detectors in unfamiliar domains can result in a significant drop in performance. This drop is due to the domain shift caused by variations in lidar, geography, or weather, which differs from the data that the detectors were trained on. For example, using a detector trained on a 32-beam lidar dataset on a 64-beam lidar shows a significant performance drop compared to using a detector that was trained specifically on that 64-beam lidar and deployment environment. This is also observed when training and testing 3D detectors across various lidars and environments. We present an auto-labeling solution that uses pre-trained detectors to generate high-quality labels for training any detector on a variety of lidar types. Similar existing methods use the prediction of a single detector to generate labels. However, relying on a single detector can lead to highly varied results on different lidar types depending on the detector architecture and its training dataset. The best detector trained on one lidar dataset may not necessarily have the best generalization performance when tested on another lidar dataset. Even if you use the most optimal detector and source dataset pair for a target domain, it may still fail to detect many cars. However, we show that building an ensemble of detectors with different architectures and source datasets can lead to a stronger set of initial pseudo-labels. This gives us a better starting point with more accurate boxes and higher recall for our auto-labeling framework. We use multi-frame pre-trained detectors in the ensemble as we show that they greatly increase the baseline performance of pre-trained detectors on a variety of testing domains. Their cross-domain performance is even higher than some self-training works. To refine the initial pseudo-label set, we use a temporal refinement strategy to increase label recall while maintaining precision. This consists of a few key concepts. In human perception, identifying certain objects from a distance or when occluded can be challenging. To address this, our eyes continuously track the object until its class can be confidently determined. Likewise, to improve label precision, we withhold the use of tracks as pseudo-labels until we obtain confident detections above a threshold. For vehicle labeling, we focus on labeling static vehicles since a few strong detections of a parked vehicle allows us to address missing detections and refine less confident predictions for the entire sequence. Because static and dynamic vehicles share the same appearance, this approach also allows a 3D detector to generalize to dynamic vehicle detection. For pedestrians, pole-like objects tend to be frequently misclassified as pedestrians with a similar confidence score. However, it is obvious that the object is a pedestrian if it is moving. Therefore, we initially use dynamic pedestrian tracks as labels to increase precision for the pedestrian class. Through multiple rounds of label refinement, we find that this also improves the detector's generalization to static pedestrians, since dynamic pedestrians may not always be moving. We demonstrate that MS3D++ obtains state-of-the-art performance for 3D object detection on multiple datasets without any human-annotated labels. The performance is even comparable to training with human-annotated labels in bird's-eye view detection. In summary, MS3D++ automatically generates labels to train a 3D detector on a range of lidar types, regardless of their density. Our ensemble can be tailored with any 3D detector and source domain pair, therefore making it a versatile solution for a wide range of lidars and scenes. The final set of labels can be used to train any 3D detector with any data augmentation technique on the given target domain. On a broader scale, MS3D++ is a cost-effective solution that facilitates the deployment of cutting-edge 3D detector research across a range of present and future lidar technologies. See our GitHub page for more information.